All right, look like it went live. It also looks like there's about a 10-second lag, which I can't really do anything about. So I'm mainly just gonna have you guys let me know what you want to go over. So my thoughts were, by the time we got to this help hours, that you guys would have taken the third test, and nature decided that that wasn't going to happen. So my plans were just to go over homework 7. I can still touch on stuff from the concept from the third test if there's enough people that want to go over it. But for right now, my plans are just homework 7. I'm still voting, going over the homework. All right, sounds good. I'm going to wait a few minutes. I'm not really scheduled to start till 10, so I'm going to wait, let a few people file in. So, got one vote to go over the homework. Is it good if I just start on problem 1, or is there another problem that other people really want to touch on? Just go over the homework. Just go through the homework. All right. So I'll just give it a few minutes, let people file in. This is kind of a shorter homework assignment, but I'll warn you that the second problem is a bit of a beast. We're also hoping that this format works out better than Google Hangouts. The way we're doing it here, I'm hoping it's going to be recorded, so I'll have it uploaded later, and I'll send the link out later, and I'll try and keep all of our videos in one playlist just so that it's easy for you guys to find it all. All right, 10 o'clock, so I'm going to get started on problem 1. Get this. So, number 1, calculate the steady states for the following elementary liquid phase reaction and data below, carried out in a CSTR. And part A, what are the steady state temperatures and conversions for this reactor? All right, so since we know that it is a multiple steady states problem, we're going to have a couple different answers. And the graph that we're going to make is going to end up looking something like, let me pull it up. Something like this, where we're going to have to plot the conversion of the energy balance and the conversion of the mass balance, both as functions of temperature. So, since we need to get the conversion, so we need x of the mass balance as a function of temperature and x of the energy balance as a function of temperature. So let's start with the mass balance one. I'm going to move over here to do this. So when we're doing a mass balance on a reactor, best place to start is the design equation. Balance over minus RA. And actually for this reaction, we can see that it is 1-to-1, A to B in the reaction. But we see that Ca naught is 20 and Cb naught is 3. So B is limiting. So I'm just going to change that over here just so the nomenclature makes sense. All right. For B, for the reaction rate, we're told that it is elementary and liquid phase. So minus RB is equal to a rate constant K times Ca times Cb. And remember that for a liquid phase reaction, Ci is equal to Cb naught times theta I times, minus nu I over nu A times xb, where I'm just using B in this case to represent our limiting reactant. Oops. So we can write this. So for Cb, this is going to be equal to Cb naught, and theta B, since B is the limiting reactant, is just 1 minus xb. For Ca, it's going to be equal to Cb naught times 20 over 3 minus xb. So that's going to make minus Rb equal to K Cb naught squared times 1 minus xb times 20 over 3 minus xb. Let me just take a look at what we have. All right. That should be good. So our energy balance, mass balance, sorry, V equals FB naught times X and B is equal to K times CB naught squared times 1 minus X and B times 20 over 3 minus X and B. And remember that we're trying to get X as a function of temperature. So we've got to consider temperature. We have to include temperature considerations for this. And from what we're seeing here, the only term that's going to be in terms of temperature is going to be our reaction rate constant K. Zoom in so it's not so awkward for me. And we know the relationship of K with temperature. We're given it right here. Make sure I write it correctly. So now we can rewrite it so that V is equal to FB naught times XMB over our expression for K, 20,000 for RT, one minus XMB times 20 over 3 minus XMB. Not the neatest, but here is the mass balance that we're going to want to solve in order to get the conversion of the mass balance as a function of temperature. And I'm going to leave it like that for now. I'll show you how to, because I'm doing this all on computer, I can show you guys how to solve it, but I'm going to leave it like that for now. So, moving on to the energy balance. Go up here. So best place to start is just the entire energy balance. Dot times XEB minus FB naught theta I CPI times T minus T naught. And then start canceling out terms. So we know we're at steady state, so our differential goes to 0. We know we have no shaft work, so that goes to 0. Is this a jacketed reactor? Does it explicitly say that? I don't know if it explicitly said, but we are given U and A terms. We're given a UA term. So that's going to make, that means that this is a jacketed reactor. So Q dot is going to be equal to UA times temperature of our cooling medium minus T. So, making those substitutions, solving for a few things, we have that 0 is equal to, oh my god, that was bad, UA, TA minus T over FB naught minus delta HR XEB minus theta I CPI T minus T naught. Katie said we can assume it. Okay, yeah. All right. So looking at the terms that we have here, we know essentially everything over here. Since we're not told what delta HR, so normally delta HR is equal, at temperature T is equal to some delta HR at a reference temperature plus delta CPI times some change in temperature. In this case, delta HR is just given. It's not given at a reference temperature, so we're just going to assume that delta HR is not a function of T. And or that we can assume delta CP is 0. For this sigma theta I CPI term, we're given what we're given this term right here times CB naught. So basically, this term is just going to be equal to what we're given, this sigma theta I CPI times CB naught over CB naught. And we can solve this equation directly for our energy balance conversion as a function of temperature. And there is our energy balance equation. And if you were to actually carry this out a little bit, you'll see that it's actually linear. That XEB is linear as a function of T. All right, so we've got our energy balance, we've got our mass balance. So now the next step is to go and plot these. And since I'm doing this on a computer, I can show you guys how to do that. So I got, excuse me. I have Python pulled up, just run that. Importing the stuff we need. Everything in here is our constants given in the units that, and I've made all the unit conversions that we need to make. There we go. So now we just need to plug in our equations for our energy balance and our mass balance. So in this case, the easy one is the energy balance. So I'll start with that first. So I've got my energy balance, and I'm just going to use this lambda notation because it's a little simpler. Basically what this does, this lambda says like whatever my independent variable is, in this case XEB is equal to lambda, which is telling it create a function, and whatever comes after that is my dependent variable, or my independent variable t. So now I just plug in the equation I solved for before. Essentially this guy right here, I'm just going to plug him in. All right, hopefully that works. And then we are going to, in this case for our mass balance, we have X in 3 different locations. And because it's in 3 different locations, it's going to be very, very difficult to solve for it directly the way we did up here. because on the bottom, it's going to give us like a quadratic. So in this case, to solve for the conversion as a function of temperature, we're going to want to use fsolve. So in this case, we're going to do the full notation. So we're going to have x and t. I'm going to have k in there so it's not so cluttered. And then remember that fsolve is going to solve for whatever unknown I have, in this case x m of b, such that this, my left-hand side and my right-hand side are equal, or that v minus this whole thing is going to be equal to 0. So I'm gonna just put some dummy variable, which I'll just say is m. I got v minus my whole right-hand side. Make sure I get this in right. Over. All right. And we're going to return m. All right, the problem statement says that we are looking in the temperature range of 310 to 375 Kelvin, and we'll do it for 1,000 points for the fun of it. In order to get our, using that lambda notation, in order to get our the conversion of our energy balance, our solution, it's just going to be xEb of t, and that's it. That will plug in this t into the t's we have up here, because everything else is a constant, and then it'll give us an array of conversions. So energy balance is done. On to the mass balance. So we're going to start off with a guess of 0 for our initial conversion. And I'm going to make just an empty array for our solution. And with fsolve will only solve for our solution at one point. And because of, but we don't want to do it at one point, we want to do it at 1,000 points. So we're going to have to put it into a for loop. In range of 0 to length t. So our solution is going to be equal to fsolve of my function. I put in my guess of the thing I'm trying to solve for, and because our function had 2 inputs, but only one of those inputs is an unknown, we're going to use this argument, oh no. Why is it buffering? Is it coming through? I just want to make sure, because on my end it just completely stopped. Oh, it did. Okay. Sorry about that. It didn't look like it was going through. Okay, so minus that little panic attack. So here is how we're going to solve for our mass balance. We can see that I need to reset the guess every time so it can actually go and solve for it. And that should be everything. So if that worked, we should be able to plot our solutions now. Equal to x equals b. I don't need to make it look as pretty. Oops. Legend. Okay, hopefully this worked. I'm gonna be upset if it didn't because I'm kind of just copying old code. Let's see. And it did work. Great. So looking at this graph, you can see that we have, it looks like 3 steady states, 3 locations where our energy and mass balances are equal for the reactor temperature. Our conversions are equal at a reactor temperature. So the rest of the problem asked that you guys find the temperature and conversion of the reactor, the steady state temperature and conversion of the reactor. So essentially, at this point, what is the temperature and conversion? And then same thing for that point, and same thing for that point. And I'm going to leave that part up to you. Do we need to turn in a graph for this problem? I would say it wouldn't hurt to do so. But what's really required is the temperature and the conversion. You can turn in the graph if you'd like, but it's mainly temperature and conversion. We can see if you did it right based off of the values you give us for temperature and conversion. So, yeah. So the rest of it, I'm going to leave up to you guys on interpreting this graph on finding temperature and conversion there. And then part B, are there unstable steady states? And if so, which ones? So remember that for an unstable steady state, that the heat generated is at a steady state if the heat, and you increase the temperature, if the heat generated is greater than the heat removed, that is considered an unstable steady state because you're making more heat than you're removing. Where is it? And if you remember back to other examples, that if we go back here, in general, the heat removed is the linear line. So, going back, we can see that our linear one is our energy balance, so that's going to be the heat removed, making the mass balance the heat generated. So if we look at this steady state and we go slightly higher, just sure, at that point right there, which is higher, our heat removed or our heat generated? Well, we're seeing that our energy balance is higher. So our heat removed is higher as we increase in temperature at that steady state, meaning that this steady state is stable, that bottom one on the left there. We go to this one. again, increase in temperature a little bit, we can see that our mass balance, or the heat generated, is greater than the heat removed, making that one an unstable steady state. And then likewise, if we go to this one, we can see it's going to be very, very similar to the one at the bottom, meaning that, the one at the top is going to be very similar to the one at the bottom, meaning that one is a stable steady state, meaning that you only have one unstable steady state, and it's that one in the middle. Which homework is this? This is homework 7. All right, and that pretty much covers it for problem 1. Any questions on that? And I think I saw a question about whether or not homework 7 was still going to be due on Wednesday, and it is. I know it kind of sucks. It seems like you guys got a lot of tests next week, but we got to maintain some kind of schedule. All right, any questions on this one? If not, I'll move on to problem 2. Give me 1 second. All right, so sorry about that. Moving on to problem 2. This will load. All right, the elementary liquid phase reaction A goes to B occurs in a jacketed CSTR. Species A and inert I are fed to the reactor in equimolar amounts. The molar feed rate of A, 80 moles per minute, that's FA naught, given all this information. So, part A, what is the reactor temperature at a feed temperature of 450 Kelvin? Okay. So, at this point, the knee-jerk reaction would be to start with either a mass or an energy balance, and that is a good way to go. So let's start with the easier one, the mass balance. So, and as always with the mass balance, we start with the, let's start with the design equation. The mass balance over minus RA. We're told it's elementary liquid phase with, and it's just A goes to B. So minus RA is equal to K times CA. Rewriting that in terms of conversion, we get K times CA naught times 1 minus XA, or I guess X MB. In this problem, we're not really told anything about either an inlet volumetric flow rate or an inlet concentration. So I'm going to rewrite CA naught in terms of the molar flow rate, which we do know, and the volumetric flow rate, which we don't know, but we'll be able to get rid of. So we have V is equal to FA naught times X MB times V naught over K times FA naught times 1 minus XMB. Where that V naught, that was on the bottom, just went over onto the top. So we can cancel out our flow rates, and we end up with this. And like I mentioned before, we don't really know anything about the volumetric flow rate. And we also don't know anything about volume, actually. But we do know what tau is. Tau is given. We know, yes, equal to V. Tau is equal to V over V naught, or V is equal to tau times V naught. So now we can make that substitution. So we got X MB times V naught over K times 1 minus X MB is equal to tau times V naught. Now our V naughts cancel, and we end up with XMB over K times 1 minus XMB is equal to tau. And then, because this is a non-isothermal system, we need to consider what factors here are going to change with temperature, and in this case, it's going to be K. K is a direct function of temperature. And in the last problem, we were just given the Arrhenius equation and all the constants that we needed in order to solve that. In this case, we are given K at 350 Kelvin. We're given a reference temperature. So we'll have to use the expanded form of the Arrhenius equation to get K at 350. R over 350 minus 1 over T. I hope I did that right. I sometimes get it backwards. Hopefully that equation is familiar to you. But that's all we need for our mass balance. So let's move on to the energy balance. So I like to start with the entire thing. That's FA naught delta HR X A minus A naught theta I CPI T minus T naught. All right, we're assuming steady state. We're assuming no shaft work. We are told it is a jacketed reactor, so Q dot is going to be equal to UA times TA minus T, where TA is the temperature of our cooling medium. Rearranging and making the substitutions, we get that 0 is equal to UA times TA minus T over FA naught delta HR X, and I'm going to call not XA but XEB minus theta I CPI T minus T naught. All right. Sorry. Okay, so what terms do we know or do we not know? We know UA, we know TA, we know FA naught. We are similar to the last problem. We're just told that delta HR is just given. It's not given at a specific reference temperature, so we're going to assume that delta HR is not a function of T and therefore a constant. So we're just gonna, and we are given that, and we're given T naught. We don't know this yet. So we got theta I CPI. It's going to be equal to theta A CPA plus theta B CPB. And don't forget that we have an inert, so we have a theta I CPI. We can assume that, or we don't need to assume because we're told that only A and I are fed to the reactor, so that makes theta B 0. Theta A, since A is the limiting reactant, theta A is always 1. And theta I, since it says A and I are fed in equimolar amounts, theta I will also be 1. So this term ends up just being theta I CPI. It's going to be equal to CPA plus CPI. And I'm just going to plug in the numbers here. So theta A is 20 calories per mole. Oops. And CPI is 30. So it's equal to 50 calories per mole degree C. All right, now I'm going to, based off of this energy balance equation, I'm going to resolve it in terms of the conversion. So XEB is equal to 1 over delta HR times ST over FA naught minus, and then that sigma theta CPI term we just found to be 50 calories per mole degree C times T minus T naught. And if you remember, in the energy balance we assumed steady state, and remember that at steady state the conversion of the energy balance needs to be equal to the conversion of the mass balance. So going back up to our mass balance up here, we see that we can plug in what we just solved for equal to X and B over K times 1 minus X MB, where XMB is equal to this right up here. Wow, and remembering that K is a function, also a function of temperature. Minus 1 over T. So now, technically, we only have one unknown, because we have written our conversion, which also technically is unknown, in terms of our temperature, which is ultimately the unknown that we want to find. And I can show you guys how to solve that. This is a problem I highly recommend doing in Excel, and you'll see why in part B. So If I can get my mouse to work, wherever it is. There it is. All right, so here's the Excel file. For the most part, all of these are just constants that were plugged in. The only one that was kind of solved for is this theta term, but that theta term is what we solved for right here. So I just put it in straight as 50. All right. So what we're ultimately trying to solve for is temperature. And we're just going to put in a dummy number right now. Let's try that. And we know that our conversion and our reaction rate constant and ultimately the mass balance are all functions of temperature. Let me zoom in. So our conversion, x, that is this xEb is equal to what was left of our energy balance equation. So we can go back over here and put that in. So UA over FA naught. Yeah, UA over FA naught times temperature minus, no, make sure I do this right, TA minus my temperature make sure I'm entering this. Minus 50 times, let me split this up. Minus my inlet temperature. No. 50 times T minus the inlet temperature. Then divide that whole thing by delta H. And sorry if that was a little confusing because I was confusing myself. Basically what this is this term right here. My this term, my energy balance equation. All right, next, K. And for K, it's just going to be that Arrhenius equation. So we've got my K at 350 times the exponential of EA over R times 1 over 350 minus 1 over T. And my mass balance is that one right there, is tau. This is the one that this is ultimately the one that's going to actually solve for our temperature. So I'm going to goal seek, I'm going to want, what I'm going to end up putting in is actually going to be this 0 is equal to tau minus xmb over k times 1 minus xmb. So I'm going to goal seek this. I'm going to enter that function in here, and I'm going to goal seek it to be 0, which will ultimately solve for our temperature. So I'm going to say, where's my mouse? There it is. Tau minus my mass balance, my conversion over K times 1 minus my conversion. And since X and K are all functions of temperature, changing temperature will change my mass balance. So I hope I did that right. Let's find out. Oops. So we're going to set mass balance to 0 by changing temperature. All right, perfect. So we see that we now have my mass balance is basically 0. It's close enough to the -5. That's close to 0. And my temperature is almost 400 degrees. So going back to the problem, what is the reactor temperature at a feed temperature of 450, where we said our feed temperature is 450, we get that our reactor temperature is approximately 400. And another good check to make sure that it worked correctly, aside from the mass balance, is to make sure that your conversion makes sense as well. So if you're getting a conversion that's greater than 1, you know that's not possible, which is an indicator that something went wrong. Okay, so that was part A. On to part B. So part B, plot the reactor temperature as a function of the feed temperature. So part B is essentially just asking us to redo what we just did at different temperatures. And when you go and make this plot, I'm going to warn you first that your plot is going to end up looking something like this. Something a little like the extinction ignition curves. And because of that, because of this, these discontinuities, you're not going to want to do this in Python, because I know a lot of you might have the gut instinct to do this in Python, but because that there's these discontinuities, as well as, if you can see in this region here, there's actually 2 solutions for one entering temperature. That's going to wreak havoc on Python as well. So my advice is to do this in Excel. And I'll show you guys kind of how I did it. So we're going to have temperatures, and I increment by 25. I think that'll show, you'll be able to see what you need to see doing it this way. 25, 450, and you don't need to go higher than 450. 450 is perfectly fine. And looking at this, you're going to have, it's kind of going to be 2 sort of independent conversions, 2 independent lines, 2 independent solutions. So you're going to have a lower branch, or I'll just say lower T, and then you're going to have an upper branch that's also going to give you a temperature. And if you remember back to problem 1, that with a new inlet temperature, and that the conversion K, our reaction rate constant, and our overall mass balance were all functions of T. And the reactor temperature is going to change with the inlet temperature, which means that we're going to have new conversions, new reaction rate constants, and new mass balances at all of these. So for a lower our lower branch, we're going to have a bunch of new conversions, and upper branch, new conversions. And then same thing with K, and same thing with the mass balance. So let me just kind of show you. Here's a good guess. We know the answer to this one already, this 450, because we already solved for it. But let me just get this ready. Okay, fine. Sorry, this is kind of an agonizing process. Oops, nope. There we go. And we're going to do the same thing for K. If we did it using G of t and R of t, is it analogous to your mass balance and energy balance setup like you are making now? I want to say that it should be. I haven't tried it that way, so I can't speak to that, but yeah, you sent me yours last night, and it was looking like it was like you were getting there. So I would say that that method does work as well. I'm just showing you the way that I know how to do it. This was a problem that I distinctly did not like. Okay. So all I've really done over here is I've taken what I did right in this first two columns in part A, and I just copied them over into this table. It's doing the same thing, but I'll have to go and goal seek each point once again. So let's go to data, go to goal seek. So it's going to work the same way, where if I set that to 0, I should be able to solve for my temperature. And it did. Cool. So I get my mass balance is essentially 0. I have a very low conversion. And I have a temperature of, I get my temperature, my outlet temperature, as a function of my inlet. So let me just put a couple guesses here. Let me get it working for this upper. Yep, that's what I want. Okay, so I'll just solve for this first point here. So, and again, we've already did this one. So, and our answers match, that's good. Okay, so I'm trying to think of the best way of telling you to do this. Because honestly, I can't think of a much better way. So in this case, you're going to have to pick a guess. So let's do this one. So I forgot what the answer was, but let's try that. So we go to goal seek. All right, so there's the answer on that one. So the problem is I've stretched this lower and upper K, X, and mass balance things for the whole thing. But the truth is that this lower T, this isn't going to stretch all the way to 450. So if we go back to the this example for the ignition extinction curve, it's going to reach a point where it's just going to explode. It's going to shoot up, and our and it's this essentially this lower branch, it just isn't going to exist anymore. So it's kind of going to be trial and error for you guys to figure out where that point is going to be. Actually, I think that's one of the problems. Another problem with this one was if your guess, like the guess that you're gonna put here, like let's pick a number, 390 again. If your guess isn't pretty close, you're likely going to have difficulties solving it. So I got it there. It still takes a while though, unfortunately. And then kind of within this area here, I believe. Let me take a look. Okay, maybe not that area. More like that area. In this area, you're going to have solutions for both of them. There's going to be a conversion and a reactor temperature for both the upper and the lower. And remember, this goes back to the extinction ignition curve that, you know, as we're slowly increasing temperature, we're going to reach a point where it's just going to shoot up to this upper branch. But even then, you can cool it back down and still remain on this upper branch. And that's kind of this gray area here. Like, I want to show you guys how it's, you know, how to do it, but I feel like I'm going to basically give away the whole problem. So there's kind of this weird in between. I'm trying to think of how to do this. But I think from here, with me giving you these first couple points, you can at least have enough to start with part B. And for part B, as long as you're able to get these points, I think, and plot them, that should be plenty for part B. I know that might be a little unsatisfying, but I don't want to like just show you what the graph looks like. I am confused how Excel will know which branch it is on. That's going to depend on the guess. So, okay, I guess I could show this one point. So that's going to depend on the guess. In this case, this one right here, let's say, let's go with 350. We can go 350 on both of them. Ideally, we should get the same answer. So we get 355. If we go over here, we should get the same thing because I used the same guess. However, since I know the solutions, I know that this point here is one of these that's within the in that kind of double area of the ignition curve. So I guess 350, but let's try a lower guess. Let's try that. Oops, nope, sorry. Oh, still didn't want to work. Let's go lower. There you go. So it's going to depend on the guess whether or not it's actually going to exist there. And honestly, I think the best way of going about this problem is not doing what I just did and going for a point in the middle, is to start at the ends and work your way up and down. Because you'll know, like, you can see that with these first 2 points, we go from 300 to 308. You can guess from going up 25 more degrees, we'd probably go up about the same amount, maybe another 7 or 8 degrees. So that should help lead, kind of your guess for the next one. So maybe because you're like, oh, went up about 8 degrees, it might go up about the same amount next time. So let's guess that, and you can use kind of that as to guide it. And it's probably going to increase about the same amount here. And then the same way over here is we decreased about 8-ish degrees, and then from 450 to 425, and then for 400 it might decrease about the same amount again. And with 375 it just so happened to work out, but eventually you'll be able to stop on like this lower branch because it's just not going to be able to solve because it just doesn't exist. And you can get that really is just going to come about from guessing and checking constantly. Just put different initial guesses until it changes, essentially. Yeah. And unfortunately, the solver isn't the best. It's going to be very sensitive to your guess. So if you're not able, so you'll have to constantly check new guesses. So there's that. Are there any more questions on graphing this one? Because as I said, I don't want to give too much away because I do want you guys to go and make this graph. But I understand that this can be a very difficult one. If there aren't, I'm just going to move on to part C. All right. Okay, so part C. Suppose that you begin with a feed temperature of 250, which you slowly increase. What inlet temperature must the reactor be heated before the reactor operates at a high conversion? What are the corresponding temperature and conversion of the fluid in the CSTR just above this inlet temperature? All right, so for the sake of this problem, I will graph this. So I'm just going to put in graph. And I'm going to remove everything. Okay. Let me make that look less bad. Okay. What cells are you putting into GoalSeek? So going back to, I'll just show part A. So ultimately what I'm trying to find is T. And I've set it up so that my mass balance, and my mass balance was, what was my mass balance? This guy right here. I know I want, the way I have it set up here, I want it to be equal to 0. And that my K, my reaction rate constant, and my conversion X are functions of temperature. So with these being functions of temperature, this also is indirectly a function of temperature. So by setting this guy to 0, this will change T. So when I go into GoalSeek, I'm not going to actually do it, but I'll just show you what I did. So I want this to be equal to 0 by changing my temperature. And yep, and that's how I did it. And it's basically the same over on that big graph, big table to the right there. Okay, so looking at this graph, it's incomplete, but this is going to be similar to what you're going to put on part B. Part C asks that we are starting with a feed temperature of 250, which we're going to slowly increase. What temperature must the reactor be heated before the reactor operates at a high conversion? What are the conversion temperature and conversion of the, what is the corresponding temperature and conversion of the fluid in the CSTR just above this inlet temperature? So looking back at this graph, I didn't go to 250. You guys don't necessarily have to go to 250, but we can see that at this lower temperature, it looks kind of linear. So we're going to just assume we're at 250, and we're going to increase until somewhere around here, we're going to jump. And it looked like someone asked, am I recording this? Yes. So YouTube is recording it. I'm gonna try and upload it all at the end, and I'll make a playlist of all these YouTube videos so you guys can come back and find them easily. Okay, so going back to this, we're going to increase until all of a sudden we're going to basically jump. And then if you go back over to our table here, you'll see that on this lower one, we have, minus that point, ignore that, we have very low conversions. So we're talking 0.0085. That's very low. But on the upper one, all of a sudden it's jumping up to 0.6, about 60% conversion. So what this problem is asking for is essentially, what is the inlet temperature of basically the ignition point? Maybe draw on the graph your mouse. Yeah, sorry, I thought, I think I turned off my cursor to show up. I'll fix that in the next one. Yeah, let me do that. Okay, as I mentioned before, it's not, you guys don't need to go all the way to 250. 300 will be enough to show, but we're starting at 250, which let's assume is somewhere down here. And then we're going to increase it until at a certain point, we're all of a sudden just going to shoot straight up. And part C is essentially asking, what is that point? What is this inlet temperature that this ignition occurs at? And that is going to involve more guessing and checking based on this table that we found over here. And I'll give you a hint on this one. It's going to be between these two temperatures. So somewhere between 400 and 425 is going to be the ignition point. And then for kind of the last part of part C, it asked for what is the corresponding temperature and conversion of the fluid just above this inlet temperature. So we know that at the ignition point we're going to jump up. At the ignition point we're going to jump up to this this upper curve up here. And at a temperature slightly higher than that, at an inlet temperature, so this is the, sorry, I didn't label this, inlet T, and an inlet temperature slightly higher than this point will be on this upper curve. So the rest of part C is what is the temperature at this point. It's going to be somewhere there. Basically, just read it right off the graph. And what is the conversion at that point? And when you go and actually find the temperature, the way we have it set up here, when you find the temperature at this point, you're going to have to find the conversion at the same time. So that's kind of what that problem is asking for. What is the ignition point? And if you go slightly higher than that ignition point, what is the reactor temperature and conversion? Will it be visible when we finally create our graphs? Trying to think of the best way to say it. It'll be apparent kind of where it's starting to explode there. It's not, but it's kind of gonna get to a point where it's gonna be like, if you go up one temperature, it just won't solve anymore. Like on the lower bound, like if you let's pretend like the answer is 415. Let's say 416, if you were to try to solve it on the lower bound, it won't solve anymore, is kind of what's going to happen. So let's say that the inlet temperature is 415, that's the answer, and for the lower bound, that temperature happens to be at, I don't know, 345. And that's just the answer, and you were able to get it to solve. But let's say at the, if we went to 416, and you went to a slightly higher temperature of 346, it won't solve anymore. And that's kind of because you've gone past the ignition point. It won't solve anymore because the ignition point is, you've gone past the ignition point and you're no longer on this lower branch. The lower branch doesn't exist after that point. So that's going to kind of be the telltale sign that you've found the maximum temperature. Or the maximum temperature or ignition point for the lower branch. Excuse me. All right, I hope that makes sense. And I will move on to part D, sorry. Okay. Suppose that the inlet fluid is now heated 5 degrees above the temperature in part C and is cooled by 20 degrees C where it remains. What will be the conversion? So, looking back at this graph, let me just erase some stuff. So I guess I can show you guys a little more. So I told you that the answer to part C was going to be between 400 and 425 is where extinction is going to occur. So let's it's gonna, something like that. That's kind of what it will look like. I guess I could just draw it. So let's say that our answer to part C was 418 for the fun of it. If we were to increase our inlet temperature by 5 degrees to, let's say, it will be over here, 423, we have gone past the ignition point, which means that we are now going to be on this line, somewhere over here. Because since we've gone past the extinction point, we are no longer now on the lower branch, only on the upper branch. But so we've increased by 5 degrees, and then it's saying we cool back down to, we cool at 20 degrees C. And that's kind of where it's going to stay. So we're going to cool 20 degrees, but we're going to be staying on this line. So 20 degrees down, that's going to be right about here. And we're going to, even though the lower branch does exist for that temperature, we haven't gone past the extinction point. The extinction point is going to be somewhere, just ideally, it's going to look something like that. And the only way we can get back down to that lower branch is by cooling it back below the extinction point. So even though we are cooling it, and we're cooling it to a point where the lower branch does exist, we have not hit the extinction point. So we know that our operating temperature and conversion it's going to be on this upper branch. And knowing that it is on that upper branch, we can find, you'll have to solve for it, that reactor temperature and the conversion. And I'll give you a hint on that one. Okay. That one is going to be, that's going to be somewhere in between those two temperatures. So let me kind of, so this will be part C. This one here will be part D. And it'll be another fun game of guessing and checking until you find the temperature. Remember, your guess is very sensitive to this problem and this solver. Ooh. All right, any questions on that one? So in D, are we looking for the extinction temperature? No, we are actually looking for, that's actually part E. So D, we haven't, so going back to the chart, we have slightly, as I said, so our inlet temperature is, we're starting with whatever we found in part C. We're increasing it slightly, and by increasing it, that puts us on the this upper line here. It's going to put us right there, based off of that operating temperature. Or based off our inlet temperature. But at this point, we're now going to decrease it 20 degrees C to around here. So now that's our inlet temperature. And by decreasing it, we're also going to be decreasing our reactor temperature. But because we haven't gone past extinction, our reactor temperature is going to remain, our reactor conditions are going to remain on this upper line rather than dropping back down to the lower line. And even though that lower branch does exist and does have values for this inlet temperature, because we've gone past ignition and cooled, but not cooled past extinction, we're still going to remain on the upper line. I hope that answers that question. So for part E, what is the feed temperature which will cause extinction for this reaction system? And essentially with this one, this is kind of another guess and check of what basically in part C, you went and found, so part C, you went and found ignition, which is the max for the lower branch. Part E now wants us to find extinction. Extinction, which is the minimum for the upper branch. So, I've just arbitrarily chosen this 375 as kind of a point, but you can see, looking just at the conversion, that between going from 425 to 375 to 425, there's kind of a big jump of like almost 39% conversion. So you can see that extinction is starting to happen. It hasn't quite happened yet because that's not quite the minimum yet. We can actually go lower. But you can see conversion starting to, extinction starting to occur. And again, it's going to kind of just be more guessing and checking to find the minimum value at which this upper branch is going to be able to solve. And your hint on this one is it's going to be between, it's going to be between these two temperatures, between 350 and 375. Part E. And I wish I could tell you that there's a better way of doing it aside from guess and check, but there unfortunately isn't. You kind of just have to get the guesses right. So if you guys can get your solvers to work and you're having just the hardest time trying to find, what these points are, you can come talk to Kate or I, and we can give you some advice, what a very good guess would be, essentially, to getting these points. Because this is kind of what I had to do last year. Because unfortunately, your solver is so sensitive that it's going to have a hard time. That if your guess isn't basically the answer, it's going to have a hard time solving. All right, any more questions on number 2? I hope seeing it in Excel, or at least kind of solved out, made sense to you guys. no questions, I'm going to move on to number 3. The easiest problem. All right. Or at least in my opinion, the easiest problem. The answer to part C should be between 425 and 450. No, the answer to part C should be between 400 and 425. All right. So, number 3. So we have a catalyzed reaction. We have did I say it was between 425 450? Sorry. No, it's between 400 and 425. I probably did. And just it's been a week for me too. All right, so number 3. So we have a catalyzed reaction, and we're trying to find the overall rate expression for part A. Overall rate expression R if step 1 is QE. All right, so first things first, we have 3 reactions. We got O2 plus 2S, where S is our surface species, our catalyst, goes to 2O.S, C3H6, plus our catalyzed species, produces our propylene. And that's our mechanism. So first we need to ultimately find our stoichiometric numbers, these fancy little sigmas. And the important thing to remember is kind of similar with how we did rate expressions before, was that no intermediates were to show up. No intermediates show up in the final expression. The final expression. And similarly, with catalyzed reaction, there should be no catalyst in the final reaction. And that's because catalyst is not, it's assisting with the speed and activation energy of the reaction, but it's not actually reacting itself. So so it should not show up in the final reaction. Or another way to think about it is you can think of kind of these catalyzed species, this O.S and this C3H6 O.S, as kind of intermediates, that they ultimately should disappear by the final reaction. So it helps to know that the oxidation of propylene, C3H6 plus O2 to acetone, C3H6O. That's essentially what the reaction is, and then balancing it, we get that. So, based off of that, we know that we need to have 2 acetones in our final reaction rate. Acetone only appears in the unbonded species of acetone only appears in 1, in number 3. So 1, 2, 3. So we can say that sigma 3 is equal to 2. We know that we need only 1 molecule of just unbonded oxygen. Oxygen only appears in 1 in the first one. And we have that. And we need 2 species, 2 moles of our propylene, and propylene only appears, the unbonded propylene only appears in the second reaction rate. So that one's also going to be 2. Hopefully that seems familiar. And we can also see that the rate determining step in this case is going to be step 3, because the other 2 steps are reversible, and step 3 is the only irreversible step. And remembering back to rate mechanisms, that as long as there is a reversible, the rate determining step will only be a reversible step if all of the steps are reversible. Since we have an irreversible step, that is not the case. So we can write this and remember that the overall rate, R is equal to Ri over sigma I. So we've got R3 over 2, which is going to be equal to K3 over 2 times concentration of C3H6OS. And the rule with catalyzed reactions, kind of similar to the rate mechanisms that we've done before, is that these surface species, these species bonded to the catalyst S, cannot appear in the final rate expression. So we need to find a way to get rid of that, basically. And we are told that we can assume that step 1 is QE. So writing that out, we are going to get that, so we have K1, I guess I should write these. We have K1 and a K minus 1, a K2 and a K minus 2, and a K3. So K1 with QE, remember, the forward reaction is equal to the backward reaction. K1 is equal to O2 times S, concentration of S squared over CT, equal to K minus 1 times the concentration of OS squared over CT. And the CT comes in, it has to do with the like the probability of species being on the excuse me, on the surface. And kind of a general rule of remembering it is whatever that the power of it is 1 less than whatever of the power in the numerator. So in this case, on this right side here, we have we have the OS squared. So we want CT to be the power of 1. If we look back up to this guy here, our S species was to the power of 1. So we put CT to the power of 0, which essentially makes it disappear. Is CT squared. CT would be squared if it was if we had 3 surface species. And like if we had 4 surface species in the numerator, CT would be cubed. But since we only have 2, and we have 2 surface species, because we're squaring them, CT will just be to the power of 1. So remember, we kind of said that our surface species, the anything bonded to the catalyst, is kind of the intermediate. So we're going to assume that right now OS is our intermediate. So we'll solve for that. We'll solve for that. That's not a 5. Oh, I'm struggling. The CTs in this case will cancel out. I don't know why I did that. There it is. We end up with concentration of S times the square root of capital K1 times O2. And that's just, we got from just doing some algebra on that guy right there. All right, but going back to this reaction up here into our rate determining step, we still need to find a term for this intermediate, the C3H6O.S. So in this case, we will assume pseudo steady state on that particular one. So pseudo steady state on that intermediate. So equal to 0, and then we go up here. So we see in reaction 2 that we are producing and consuming it simultaneously. So for the forward reaction, it's producing it, so it's going to be positive. And make sure I get this right. Times OS. And since our surface species for this one is to the power of 1, our CT will be to the power of 0. So we don't have to worry about it. And then we're consuming it in the reverse reaction. 6O.S. And we are once again consuming it in reaction 3. Go away. O.S. And then doing some algebra, solving for our intermediate species, we get that it is equal to K2 C3H6 O.S over K minus 2 plus K3. All right. So now we have an expression for C3H6O.S for that intermediate. It's in terms of another intermediate, but we do have that intermediate in terms of other things. So we're going to plug that back in. So we have R equal to K3 over 2. I'm going to plug in C3H6OS times K2 times C3H6. And then I'm going to plug in the expression for O.S, which was S times the square root of K1 O2 over K minus 2 plus K3. Oh, over 2. Don't want to forget that. Oh no, I had the 2, sorry. And is this done? Not quite. Because we cannot leave any of the catalyst surface concentrations in there. So right now the problem child is this concentration of S, which is our empty surface concentration of our empty surface species. So we'll have to do a site balance. So we know that our total sites is equal to the number of empty sites plus the number of sites bonded to oxygen plus the number of sites bonded to our acetone. And we have expressions for each one of these that we can plug in. We'll leave S because that is ultimately what we're trying to solve for. Times square root of K1 O2. Right? Yeah. And I have to plug in two things for that last one. K2 C3H6 times S times square root of K1 O2 over K minus 2 plus K3. All right, and we see we have a concentration of S in each term. So now we can go and solve for that in terms of all these other constants, or not constants, or known quantities. So we got CT plus so there's a concentration for S in terms of known quantities. And CT is a known quantity. Generally, it's found before the reaction has started, but it generally will not change. You'll always have the same number of sites, so which is why it's fine to leave that term in the final equation. So now we have an expression for S. Now we'll take this big long expression and plug it back into the expression we had before. So we have R equal to K3 over 2 times K2 times O2 over K minus 2 plus K3 times our concentration of S, which was this guy. There we go. Because I didn't want to write it again. And is it number of sites? Is this CT the same as the one from the QE analysis? Yes, it is. And is it the number of sites S, not total concentration? CT is the total concentration of our sites. So concentration of S is representative of our empty sites, basically. And then we also have the sites that are occupied by the oxygen and the acetone. So there is our answer for part A. A. All right, part B. Okay, find the overall rate expression if step 1 and 2 are QE. So, we'll zoom back in. So, we already completed the assumption if step B, if step B is QE, step 1 is QE, and we're just going to take that again because that holds true. Let me make sure I remember it. That remains true. So now let's do a QE on step 2. So step 2, we have K2 times the concentration of the propylene times the concentration of our OS is equal to K minus 2 times the concentration of our acetone, or our surface acetone species. So solving for the C3H6OS, we get K2 times C3H6 times OS. And plugging in OS, times S times root of K1 O2. Okay. So now, once again, we have our reaction rate is still K3 times C3H6O.S. Now we can plug in our new expression for the acetone surface species. My handwriting is deteriorating. Okay, and that was just plugging in what we had here into here. All right, so do we have any problem child species? Yes, we do. We have the S. So we're going to do that the same way we did before with a site balance. So our total number of sites is equal to our empty sites plus our sites occupied by oxygen and our sites occupied by the acetone. So plugging in those terms, times square root of Q1 O2 plus, oh my god, is equal to CT. And now we can take out concentration of S out of each one and solve for it. It's equal to CT over 1 plus C3H6 times O2. Let me do this right. Right, there's our expression for the concentration of S. Now we got to plug that back into our rate expression. So we have K3 times capital K2 over 2. Sorry, it's a little messy, but you get the gist of it. And that's part B. All right, part C. Write the apparent rate constant. Let me zoom in. Write the apparent rate constant K and the apparent activation energy E apparent for the mechanism in part B if OS is massy. So if OS is massy, that essentially says, so going back to the full site balance, that essentially assumes that it is so much larger, that OS is so much larger than our S and acetone species on the surface that they essentially go to 0. That any contributions from them are negligible, and that CT is essentially just equal to OS. And remember that we said OS is equal to the concentration of S times the square root of K1 times O2, which vastly simplifies our algebra for finding concentration of S in terms of known quantities. Now going back to the rate expression, K3, nope, R3 over 2, equal to K3, and we're going to use the same expression, so I'm going to start from this point here and just kind of take this big chunk of stuff. Times C3H6 times, let's move down, times the concentration of K1 O2 times the concentration of S, which now equals 2, is equal to T over K1 times the square root of K1. The square root of that, sorry. And that is what our new rate expression looks like. So for this part, we're assuming QE on 1 and 2 also. Yes, because it's asking us to use the mechanism in B. And we have that this denominator and this term will all cancel out. And there's our reaction. Reaction rate. So our apparent activation energy is essentially just going to be the our reaction rate constants right up here. So K apparent is equal to K3 K2 times 2. It's the culmination of our reaction rate constants. And to find the apparent activation energy, that goes back to kind of using the Arrhenius equation, where we can say that the derivative of the log of the apparent activation energy divided by d over dt over t is equal to the log of k, nope, this is little k3 over d1 over t plus d of log of capital K2 over d1 over t. And remembering back to the equation, I guess not the equation, but the graph of 1 over t versus log of k, that the slope is EA over R. So we can rewrite that, those differentials to be the activation energy, the apparent activation energy over R is equal to the activation energy of R of 3, step 3, plus delta HR of, or I guess delta H2, not necessarily delta HR, of the second reaction. And the reason why it's delta H for the second one, because it's a reversible reaction. And that cancels out all our R's, so we end up with the activation energy and delta H2 is less than 0. It's an exothermic reaction. Ooh. And because that it is it's less than 0 and that step is exothermic, you can say that the activation energy, the apparent activation energy, is less than the activation energy of the of our final step, of our rate determining step. And ultimately, that is what we're looking for. And that just about covers the homework. I've got to go here soon. Are there any questions, last minute questions you guys have for me that I can answer before I go? Thank you. Yes, you guys are welcome. What was I going to say? I'm still thinking I'll have office hours next Tuesday at 9 after the test. I do have a sign-up sheet for in-person office hours if you guys want that. It seems like things aren't getting better, so if you guys don't want to show up in person, I completely understand, but if you do, the option is there. I think Katie's gonna start having Wednesday office hours, and she'll be doing it this way too, so we'll try and have these uploaded for you guys. And doesn't look like any questions, so I hope you guys have a good weekend. Have a safe weekend, and I'll talk to you guys next week.